and again a plane wall. And today we will be discussing about a chart solution for a sphere. And then we are going to discuss about electrical analogy to lump rate capacity and systems with negligible surface resistance or a infinite plate with no external thermal resistance where H is infinity. These cases I will try to deal today's class. Okay, we will try to conclude this today chapter 2 completely, and next class we will start with force convection. Okay, this is my aim, and again this is my target to finish today. Now let us go to the chart solution for a sphere. Okay, so when we go to the chart solution for a sphere, whatever that details I gave you for chart solution. So when you want to calculate a temperature at the center of a sphere, Tc by Ta, theta c by theta I is equals to, you can able to find out from this chart. Okay, center temperature for a sphere of radius r0, for which you need to find out Biot number, and 1 by Biot number, once you find out, from that you able to find out the theta c by theta I for a for the central position of your sphere. You can able to find out it. Once you know this one, then you can able to find out that another one, temperature as a function of central position for a sphere. You can able to find out these equations, right? Theta by theta 0 is equals to, at any position also, temperature at any position you can able to find out theta by theta 0 is equals to by this 1 by Biot number. When you know, from this you can able to, from this Biot number and r by r0, that ratio of the temperature, x by that what we discussed, x by L. Similarly, this is position displacement, this is equals to r by r0. From that you can able to find out the temperature at any position. You can able to find it. Once you know that, you can able to find out heat loss q by qi of a sphere of radius with time. So this is also you can able to find out with this. Okay. So these three tables, these three charts are essential to find out that heat transfer analysis in case of a transit heat conduction analysis in case of a sphere. You can able to find out it. Okay. So this is something I wanted to talk today. Okay. This is the topic which I wanted to cover now, and already we did some of the problems related to plane wall, and again related to cylinder, long cylinders. And I am not going to do any problems with respect to these cases. It is a practice you need to make to get thorough and command and the subject is concerned. Okay, so with this I'll going to that new another one is nothing but, which is I didn't cover in the earlier class. I'll try to cover today. The topic is nothing but, this is electrical analogy for lumped heat capacity analysis, right? When we talk about electrical energy for lumped heat analysis, we are taken with a negligible internal resistance. Okay, when we take negligible internal resistance, the lumped heat capacity is almost analogous to the electrical analysis, right? What it means is nothing but, suppose if I close this switch, now what will happen? The thermal energy is going to be stored when the thermal is going to stored at a temperature of T0 in this capacitor, right? And when this is opened up, this is opened up, then the thermal energy is going to be dissipated through the internal resistance in this fashion, and it is dissipated to the out like this. Okay, this are not to the ground as like this. Okay, so this is about the electrical analysis with respect to lumped heat analysis. So here, how I can bring the similarity of this with respect to thermal heat analysis is nothing but, when you want to store thermal energy, I can use the thermal energy or internal energy raise is equals to, you try to raise mc, that is C thermal into T, right? This is temperature difference, whereas C thermal is equals to rho CV. All right, rho is nothing, rho into C, rho into V is nothing but, this is density into volume. The mass by volume is equals to density into volume, then is equal to mass into C. This is called as heat capacity. So this heat capacity into temperature is going to thermal energy stored, and this is in thermal point of view. Similarly, if I want to explain this in electrical analysis, this is equals to condenser storage or charge storage is equal to S is equals to C into E, where C is nothing but capacitance of the charge into voltage. V is voltage. This is equal to the same, and this is going to be this is going to be the electrical analysis analogous to that lumped heat capacity, as long as HA by rho CV is equals to 1 by thermal capacity, and again into thermal resistance, and again this is equals to 1 by Ce into Re, where C is equals to capacitance. This is what I mentioned is the capacitance, and R is equals to electrical resistance. Okay, so this is about the case which I wanted to talk to you with regard to the electrical analysis, right? Right, with to electrical analogy with respect to lumped rate capacity analysis. Okay, this is the next topic I wanted to cover about it. Okay, once this is covered, now I'm going for that, right? Next topic called as the next topic called as this one. So this is I have covered, right? Charge solution for sphere also I covered, and again electrical analogy to lumped rate capacity also I have covered, and I will be going for the systems with negligible surface resistance. I am going to talk about it. Okay, now I am going to the topic, the third topic. After this approximate responsivity of this thing I will talk about in this class itself when the time permits to me, right? So now I will be talking about the topic systems with negligible surface resistance. Okay, now the third topic I am calling as systems. Today's class I am going to talk about system with negligible surface resistance. Means or otherwise this also this is the case of infinite plate with no external thermal resistance, with no external thermal resistance, means H is equals to infinity. Okay, this is nothing but simply a steel ball which is at 200 degrees centigrade is just immersed in a oil bath which is maintained at a 20 degrees centigrade. Means what it is absorbed in case of a quenching problems. Okay, so this I will be discussing today's class. Okay, right now for this I will be taking a sketch which is like this. I'm drawing a sketch. It is like this. The I'm describing a system having infinite surface in yz direction, xy, and infinite direction in yz direction, and it is like this. The system is like this, and the system has got surface temperature Ts, the other side also Ts, surface temperature initially, right? And this Ts is equals to T infinity immediately when T is greater than 0. Okay, this is nothing but infinite with no thermal resistance. Means that since there is no thermal resistance, it quickly acquires the temperature of surrounding immediately. That is the case of it. Okay, and the description of this problem is this is of length L. The length is L. The system is of length L, and temperature at x t0x t0x for t is equals to 0. Just for sake of understanding, just I have taken t is equals to t0x for t is equals to 0, that I have taken into consideration. Okay, now I'll means right. This is the case of such surfaces such surfaces or process whose surface temperature remains constant. This is for such a process whose surface temperature remains constant for all t is greater than 0, and t is greater than 0, and it is equal to t infinity. That's what I have mentioned here. Okay, that is equal to t infinity equals to this. Now our objective is, from this I am going to get our objective is the transient temperature, determination of the transient temperature at any point, at any point inside the body, at, at any point inside the body of a system. Okay, the transient temperature at any point inside the body at any instant of time, at any instant of time. I mean to say the temperature is dependent on time only, right? Now for this I have considered a large plate in xy plane of uniform thickness L. The initial temperature distribution in the plate at t is equal to 0 is at t is equal to 0 assumed as T0x, right? The plate is now suddenly dipped in a environment whose temperature is T infinity, right? Now whose temperature is T infinity. Now we need to write it in a mathematical form. The mathematical form for transient heat conduction is equals to dou square T by dou x square is equals to 1 by alpha into dou T by dou T. This already you are aware of it. This is for a system of 0 is less than x is less than or equals to L, the mathematical formulation of it. And here the boundary conditions are T is equals to T0x at T is equals to 0 for 0 is less than or equals to x is less than or equals to L. This is called as initial condition. Okay, initially this is the condition. Now T is equals to Ts at, this is 0, right? This is 0 at x is equals to 0 for time t is greater than 0, and t is equals to, this is Ts, don't, this t is equals to Ts at x is equals to L for t is greater than 0, right? This I can say these are boundary conditions. Boundary conditions of the problem. Conditions of the stated problem, systems with negligible surface resistance. Now let us define, okay, now let us define let us define t is equals to t minus ts. It is only for convenience. Okay. Now then equation, this is one, right? Then equation 1 becomes alpha into dou square y by dou x square is equals to dou y by dou t. This is equation number 2. Right? Now this with the initial boundary conditions are, when it is considered like this, the initial boundary conditions are with the initial and boundary conditions are y is equals to t becomes t becomes y o x at t is equals to 0, at t is equals to 0 for 0 is less than or equals to x is less than or equals to L, and y is equals to 0 at x is equals to 0 for t is greater than 0, and y is equals to 0 at x is equals to L for t is greater than or equals to, since at y is equals to y is equal to 0 means that t is becomes ts, therefore y is equals to ts minus ts is equals to 0, therefore y is 0 at x is equals to 0 for t is greater than 0, and y is equals to 0 at x is equals to L. Right? This is you already, this is described here, right? So you can see t is equals to ts. Now y is equals to t minus ts. Then t is equals to ts happens when y is equal, when x is equals to 0, that is equal to 0, and t is equals to ts at x is equals to L. Therefore y also becomes 0, right? So this already you know about it. Okay. Now equation 2 can be solved by the method of separation of variables. This equation 2 can be solved by method of separation of variables, and this is solved. Equation 2 can be solved by method of separation of variables, variables. I will talk about this one now. Variables, and since y, if you see, this y is a function of t and x, right? You can see, right? It is a function of everywhere x and t. Therefore y is a function of x and t. The solution will be in the form of y is equals to function of x and g of t. This is 3, and where f is a function of x and g is a function of t alone, and substituting for y in equation 2, and substituting this for y in equation 2, we get minus 1 by f, and it is only function of x only, one variable, therefore d square f by dx square is equals to minus 1 by alpha into 1 by 1 by g dg by dt, right? So this is a form of I am bringing it into the variables, f related variables one side and g related variables other side of it. This is equation of variables, separation of variables. From that I have drawn this one. Okay. Now the variables of each side I am equating to a constant called as lambda square. If I this variables on either side I am equating to lambda square, then the equation would become, see, d square f by dx square plus lambda square f is equals to 0 and dg by dt plus alpha lambda square g alpha this dg by dt is equals to the alpha g if it comes to lambda square, and my lambda square if you bring it here, this is equals to 0, minus sign will get cancelled, this minus this will get cancelled. Now this is one thing. Now with this, if you go through that solving these equations, differential equations, now you are going to get means what the equations. I will write it again: d square f by dx square plus lambda square f is equals to 0, this one, and dg by dt plus 1 by dg by dt plus alpha lambda square t alpha lambda square g, sorry, this is g is equals to 0, 0 can be, this one can be written as m square. I'll write it as this if I consider as, this is write it as m square plus lambda square is equals to 0, then m is equals to plus or minus I lambda. This characteristic equation can be written in the form of m square plus lambda square is equals to 0, and m is equals to d square by dx square, lambda is equals to something like this. The m is equals to plus or minus lambda, and then the solution is equals to be f of x is equals to, which is function of x only, therefore f of x is equals to a2 into e to the power of I lambda x plus a3 into e to the power of minus I lambda x. This can also be written as a2 into e to the power of I lambda x can be written as cos lambda x plus I sin lambda x. You know about it, right? Plus a3 into e to the power minus lambda x is going to be this plus, therefore here a plus come. Now it is minus, therefore here minus will come. Therefore cos lambda x minus I sin lambda x, that is equals to a2 plus a3 of cos lambda x plus ia2 minus ia3 of sin lambda x. This is a2 plus a3. I am denoting as a constant a cos lambda x plus ia2 minus ia3. I am writing as b sin lambda x. B sin lambda x. Okay, this is for this one. Okay, and for g this one, the solution is going to be this solution is going to be, I can write it here if you have the solution for this. I'll write it here, sorry. For this I can write it here. This is equals to dg by dt is equals to alpha lambda square. This is 1 by g, and dg by g is equals to alpha lambda square t, that is equals to, I am finally writing that equation, that is g is equals to c into exponent minus alpha lambda square t. Why? Because it can be written as, since it can be written as lng is equals to alpha, this is equals to dt, this is dt, this is equals to, I write it dt, therefore this is equals to alpha lambda square t plus ln constant a. Okay, this is written as, that is equals to ln g by a is equals to alpha lambda square t, that is equals to g by a is equals to e to the power of that equation. Now you can write it as this equation, you can write it. That's how this has becomes this form. Okay, clear? This is minus, right? Minus this is equals to minus alpha square. Therefore, e to the power minus alpha lambda square t, and g is equals to C, G instead of C, J, I will use A here. This is A here. Therefore, C into e to the power of minus alpha lambda square t. This is solution. You can have it. If you want, you can remember this one. Okay. This is something like you can use it, right? And this is what I will write it as here. G is equal to, this is the solution, right? This is the solution, and f of x is equal to, this is the solution. Therefore, this is now f is equal to this one. Therefore, these are all being derived for temperature. Therefore, y is equals to y t minus ts, right? T is given as t minus ts. Y is equals to a cos lambda x plus b sin lambda x into c e to the power of minus lambda square alpha t, right? That is, it is also can be written as e is nothing but exponent to the power of minus lambda square alpha t into this multiplication. I will see if we bring it here. Then c into a, that is equal to c1 cos lambda x plus c2 sin lambda x. Another constant I have introduced here. This is number 4. Okay, this is equation number 4. Now to this, I'll rewrite this one. Y is equals to exponent of minus lambda square alpha t into c1 cos lambda x plus c2 sin lambda x. Right, now apply boundary conditions. That is, y is equals to 0 at x is equals to 0 for time greater than 0. That is equals to, if I apply this one, y is equals to 0, this is equals to 0, right? Exponent, this is equals to this is equals to c1, and this is 1. Anyway, this is 1. Therefore, and this is equal to 0. Therefore, this is equals to c1 exponent to the power of minus lambda square alpha t, right? Implies, see, This is time is greater than 0, therefore it cannot be 0, therefore C1 implies C1 is equal to 0, right? This is one first condition. Now this is first initial condition. Now I am going to second boundary condition. What is that? Second boundary condition is y is equals to 0 at x is equals to L for t is greater than 0. Now when I apply the second boundary condition, this is equals to what will happen? C2 sine lambda L, C2 sine lambda L. Anyway, C1 is 0, therefore C2 sine lambda L into exponent of minus lambda square alpha t is equal to 0. Right? If C2 is equal to 0, C1 C2 is equal to 0, then there is no solution, right? Therefore, now what I do, C2 cannot be 0, therefore sin lambda L is equal to 0 I can use. And this is also t cannot be 0, therefore this is also cannot be 0, therefore only sin lambda L is equal to 0 from this equation. Now therefore sin lambda L is equal to 0, as per sine law you know that lambda is going to be n pi by L, where n is equals to 1, 2, 3, dash, dash, dash. Okay. Since n is not equals to 0, right? Therefore, n is equals to 1, 2, 3. Right? You clear it. This is solution for sin lambda L. Okay. Right? Now the solution 4 becomes this is also 4, right? This is equation 4, I believe, right? Am I correct? This is equation number 4, right? The solution would become y is equals to sigma n is equals to 1 to infinity Cn of exponent minus lambda square alpha t, but however, right, I'll remove it here, this lambda square, this I'll rewrite it, lambda is also already it is there, therefore this is equals to, this I'll use square bracket, this is also a square bracket I use exponent minus n pi by L whole square alpha t, right, into sin n pi by L x. This is equation number 5. Okay. Now, if I apply initial boundary condition like y is equals to y0 x at t is equals to 0, at t is equal to 0, this is equals to y0 x is equals to, if I use at t is equal to 0, what will happen? This is equals to 1, therefore sigma n is equals to 1 to infinity Cn sin n pi Cn sin n pi by L into x. Okay, this looks like Fourier sine series. It is looks like this looks like this equation looks like Fourier sine series, and the value of Cn would be this, the y0 of x is equal to sigma n is equals to 1 to infinity Cn sin n pi by L into x. Looks like sine Fourier sine series. The value of Cn would be, for this, the value of Cn would be 2 by L into integral 0 to L y0 x into sine n pi by L sin n pi by L x dx. Okay, this is solution for it. Okay, and this is equation number 6. Okay, now substitute Cn in equation 5. You will get y is equals to 2 by L sigma n is equals to 1 to infinity into exponent minus n pi by L whole square alpha t into sin n pi by L x. This is 1, which is nothing but you can check it here. Here, 5, equation number 5. This is equation number 5. Okay, this is, you can check here. This I have written here, right? This one, and I am writing Cn now. This is, everything is over. Now I am writing Cn, right? Into integral 0 to L 2 by L. Already I have taken it. This is equals to 0 to L and y0 x into sin n pi by L into x dx. Okay, this is equation number 7. Okay. Clear? Now from equation number 6, initial temperature distribution is y0x. Here we know this initial temperature distribution y0x is must be known before you try to find out complete this is to be known if you want to find out the temperature at any point of at any time, right? At any point and at any time. Therefore, now this is the case. You can remember it here, or otherwise I can write it as y by y0 is equals to, I rewrite it as 2 by L into sigma n is equals to 1 to infinity exponent of minus n pi by L whole square alpha t into sin n pi by Lx into integral 0 to L sin n pi by L x dx. Okay, 0 to L. This is the equation. You must remember it, right? Now for the special case of a plate, now I'm going for the special case. For the special case of a plate, initially at a uniform temperature y0, equation 6 reduces to Cn is equals to 2 by L integral 0 to L y0 sin n pi by L into x dx, that is equals to, this is written as 2 into y0 into divided by n pi into 1 minus cos n pi. Right, this is one case. Special case, for special case of a plate, initial at a temperature of uniform temperature of y0, so t0 minus ts, equation 6 reduces to 2 by L 0 to L y0 2 y0, this is y0 by L. I will keep it here, and this is equals to integration of this one. I can write it as 1 minus cos n pi by n cos n pi, and this is equals to n pi is coming here, that n pi by l, the l gets cancelled, that is 2 y naught by l, right? And this is equals to, and this is going to be 4 y naught by n pi when n is equals to 1, 2, 3, etc. And we know, right? This is equals to 0, means what? Cn is equals to 0, that is Cn is equals to 0 for n is equals to 2, 4, 6, etc. Okay, then means what? This is not applicable to me, therefore y is equals to y naught into 4 pi by into sigma n is equals to 1 to infinity 1 by n into n pi by x by l into exponential of minus n pi by l whole square alpha t n is equals to 1, 3, 5, etc. or y by y naught, if y naught comes here, y by y naught is equals to, this can be written as t minus ts by t0 minus ts is equals to 4 by pi, this is 4 by pi sigma n is equals to 1, 3, 5 to infinity 1 by n into sin n pi by l into x exponent minus n pi by l whole square alpha t. This is equation number 8. Now, if I want to find out, this is temperature distribution at any the ratio of temperatures. You can write it here, right? Now once you know this one, now if I want to calculate heat transfer, now Q, heat transfer Q with respect to x direction and the time t is defined as minus Ka. Since it is 1 times dt by dx, I will write it. This is equals to, if I t, this is the equation, right? If I integrate this, if I differentiate this one, I am going to get 4 Ka by L into Ts minus T0, right? Ts minus T0 minus, in order to remove minus, I have changed this one, T0 minus Ts, instead of this, I write Ts minus T0 into sigma n is equals to 1 to infinity cos n pi by L into x exponent of minus n pi by L into x n into alpha t. This is number 9, equation number 9, right? This is heat transfer at any time, right? And now if I want to calculate the total heat quantity, the total quantity of it, the total quantity of heat U given off during a time interval which is 0 to t, initially 0 and again t is is obtained by integrating equation 9, that is equals to u total net, no total quantity, u xt is equals to 0 to t q x t dt, that is equals to, the solution I am writing into equation, right? 4 by pi square into KAL into Ts minus T0 into sigma n is equals to 1 to infinity 1 to infinity 1 by n square into 1 minus exponent of minus n pi by L whole square alpha t into cos n pi by L into x. This is equation number 10, right? And this is equation number 10. Now the temperature distribution at the center of the plate is, that is at x is equals to L by 2 is going to be Tc minus T infinity. Tc is center of the plate divided by T0 minus Ts is equals to T0 minus Ts is equals to 4 by pi sigma n is equals to 1 to infinity 1 by n into exponent minus n pi by L whole square alpha t into sin n pi by 2 and n pi by L, right? This is equals to thus n pi by L. This is equation number 11 or 88. This is equation number L and n is equals to 1 2 3 4 1 3 5 something like this. Okay, so this is about the system with infinite infinite surface resistance. Okay, so H is equals to infinity. So this is the case which we wanted to discuss about in this class. Okay, so far, right? So far we have discussed the transient heat conduction transient heat conduction related problems, right? Now these are all we have discussed so far. All right. Now the last one is nothing but the fourth one I will be discussing about is nothing but uh, response time of a thermocouple. Just let me check. Right. Fourth one, response time of a temperature measuring equipment. This I will be talking about. Okay. Now I'll go to that fourth topic. Now fourth topic today. Time of a temperature measuring equipment. Okay, this I will be talking about today. Right? So the normally the temperature measuring instrument equipment is going to be thermocouple or thermometer. Okay. Now the thermometer, how it is measures in a bit by a principle of equilibrium. It works on the principle of equilibrium. Means what? Suppose a thermometer is taken and it is at not in equilibrium with the system whose temperature is to be measured. Now this thermometer is brought in contact with it. After some time, an equilibrium is attained, and the temperature, and then it attains the both system and the thermometer is attains a thermal equilibrium. That is shows the indication of thermometer, the reading on the thermometer, that is called as temperature. Okay, that we know in principle about it, right? Now the response time of a temperature measuring instrument is nothing but, now we want to measure the temperature of a system as quick as possible. Means what? The sensitivity we'll talk about. Okay, we talk about sensitivity. Okay, sensitivity. To have this as quick as possible, we know that what is that formula we have used in it? T minus T infinity by T zero minus T infinity is equals to e to the power of minus HA by rho CV into T, right? So lumped heat, this analysis is not this is related lumped heat capacity, right? So in the lumped heat capacity analysis, this response, this T, right? If you want to be means that the response time as quick as possible, this has to be infinity, right? This HA by rho CV is to be uh, no infinite. Therefore, to have it means what is rho CV by HA by HA T by rho CV T should be large. Should be large. So, right. To make this exponential should be uh, when it is going to be very large, what will happen? It reaches to a zero value. When it reaches to a zero value, the response time is very less. To have it, what you how do you know about it is not well? Either this should be rho should be small, and otherwise C should be small, or V by A should be as large as possible, right? V by A should be as large. This one should be as large as possible. Okay, right. So means this can be achieved by decreasing the diameter V by A, decreasing diameter or length increase. Okay, therefore, so therefore what I mean to say is nothing but, so this should be as large as possible. This you can make it as large as possible by increasing h or by increasing v by a, or reducing rho and reducing c. Therefore, right, therefore what I mean to say is nothing but, let's this ratio ha by rho cv is termed as a function of time t, right? Then this is equals to t minus t infinity divided by t zero minus t infinity is equals to, I can write it as e to the power of this is t, this I written as 1 by t, this is equals to 1 by t, this rho cv by hal written as t star, therefore e to the power minus t by t star is equals to e to the power of minus 1. This is equals to 0.368. 0.368 means what? So this t minus t infinity is equals to 0.368 into t0 minus t infinity, or if it is initial temperature, this is surface temperature. Okay, so as this should be means what? It should be quickly, the difference should be 0.368, or otherwise, right? T0 should be as fast as possible. Means this temperature difference would reaches to 0.632, difference of this 0.632. Therefore, now I'll try to define the sensitivity. Are you following right now? This is t minus t infinity t0 over t infinity is equal to e to the power of minus 1, that is equal to 0.368, right? Now this means uh, this means initial temperature and the final temperature should be, the temperature difference should be body temperature 0.368, or otherwise it should the system should quickly reach to 63.632 times the surface temperature as quickly as possible, or otherwise this is nothing but the time required, the how quick this is respond to this, reach to this condition 0.63 times the initial temperature. Sorry, this I'll write it here now. Once you know this difference, I mean 1 minus 0.368 is equals to 0.632. That I mean to say the time required. Now I will be going to define sensitivity. Sensitivity. This is nothing but the time required by a thermocouple to reach 63.2% of the initial temperature difference. Initial temperature difference is called sensitivity. I will talk about this now clearly. Okay, right? So what is sensitivity is nothing but the time required by a thermocouple to reach 63.2% of the initial temperature difference. Initial temperature difference is called sensitivity. Initial temperature difference is nothing but T0 minus T infinity. Right? Now, means if I immerse a thermometer, it should quickly respond to this initial temperature difference. 63.2 times the initial temperature difference. So how quick it respond based on this, I can say the thermocouple is going to be sensitive. So therefore, to have a thermocouple, one should have a small diameter of a wire, but of longer length is required to measure the accurate measure of a thermometer. Right, accurate measure of, or otherwise, this thermometer is going to be more sensitive, or otherwise easily attain temperature of the system, right? Therefore this is gives something about that. What I mean to say is nothing but the measure of thermal resistance, right? Response time which is required for this. Okay, normally the response time we take it is nothing but, as I said, this is T star. I mentioned is nothing but, what I mentioned is here e to the power of minus HA by rho CV into T, no, rho CV into T. In that, this I have treated as HA by rho CV minus HA by rho CV, or else rho CV, sorry, or else rho CV by HA is treated as T star. Okay, this is also time constant. Therefore, T by T star is equal to 0. Therefore, the temperature measurement should start, the thermocouple should start taking readings only when it reaches a 40 star time period. When it reaches a 40 star. Normally, the time allowed, let me check once, the time allowed for the temperature varies from, for thermocouples, the time allowed, or rather the time constant for a thermocouple varies from 0.04 seconds to 2.5 seconds. Okay, this is about the case which I wanted to talk about at the final response time of a temperature measuring instrument. Okay, so the response to time of a temperature measuring instrument, normally the temperature measuring instrument is thermocouple or thermometer. The thermocouple or thermometer, how quickly it is attains the equilibrium with the with the system. So to attain the equilibrium with the system, what are the your requirements is going to be? If I write here e to the power of minus HA by rho CVT, the exponent should be to become 1 minus 1. What I'll require is nothing but this HA by rho CV as large as possible. To have HA by rho CV as large as possible, the options I'm having is nothing but either I can increase H, or otherwise V by A I can increase it, right? So or otherwise I can reduce rho and I can reduce capacity thermal, or otherwise rho C is going to be what is called as density into specific heat, right? This I can reduce it. Ultimately, I can get e to the power of minus HA by rho CVT is going to equivalent to 1. When I get it is equivalent to 1, that is going to be get the value e to the power of minus 1 is going to 0.368, right? Means what? T minus T infinity, T minus T infinity, T0 minus T infinity is equals to 0.368. Therefore, T is equals to, if I use this one, T is equals to, what I am going to get is nothing but 0.632 times 0.632. So therefore, the response time required, I'll define as the time required for a thermocouple to reach a initial temperature difference of 63 point time is called as a sensitivity, right? So as less is the time, this is more is going to be sensitivity, all right? That is going to be my objective, right? So in order to have a more sensitivity in the thermocouple, I will be using a thermocouple which is of a smaller dia and of that means a wire is going to be used, thermocouple in the form of a wire. I am going to use normally the wires of small dia is of small dia and again longer length. This is the concept I will be using uh, 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 in case of a thermocouple measurement or temperature measurement cases. Okay, so with this, I'm going to cover. I have completed all the chapters related to Unit 2 and Unit 1. Unit 2 and Unit 1. And the next class, I will be going to discuss the topic. I'll show you the topic which I'm going to cover in the coming classes. Let me go through the topics I need to cover. I think I do not have that. Yeah, I'll. Okay, this I'll keep.